Look at this here. And again, we're going to use basically our formula. We're going to take our percent abundance of our first element times the atomic mass of that first element, our isotope. Again, remember, as I mentioned, you go and plus it here or add percent abundance of our second one times the atomic mass of our second. And again, if you had 3 or more, or however many, you will go through it. So here we have our 2 isotopes. And once again, it's always a good idea to just kind of quickly take a peek at the percentages and make sure that it does add up to 100. And again, like I said, it may not be 100 like perfectly on the nose, but it should definitely be in the ballpark of 100 in terms of the percentages. And we have that here. So we're going to do our atomic mass here. And we're going to take our first isotope. I can go with the 79. And I'm going to just move the decimal point 2 places to the left. So that'll give me 0.5070, again, converting our percentage into a decimal. We're going to multiply that by 79.92 AMU. Again, we're going to add it now to our second isotope here. And once again, you can move the decimal, or you can multiply by or divide by 100 to do it for you. And we'll do that there as 0.4932. We're going to times it by 80.92 AMU. And again here, we're going to pop that into our calculator, 0.5070 times 7992. I would personally hit equals at this point and then hit the plus button, open a parentheses, 0.4932 times 80.92. That's going to give us here an 80.43 AMU in this case. And again, you can see that's slightly different than what you see on the periodic table of 79.90, but again, it's in the ballpark here of pretty close to it. Now, any questions on that? And obviously, some of the difference does come from the percentage rounding and the AMU rounding of the isotope. Things like in nature, so all these are basically the naturally occurring isotopes for these elements. So for example, like we were talking about carbon there, it has carbon 12, carbon 13 that's naturally occurring. And that's the percentage of how one isotope occurs versus the other. So just take that, for example, the carbon one was carbon 12 and carbon 13. If you were to find carbon 12 or carbon atoms in nature naturally, it would be about 99% of the time you're going to find a carbon 12 isotope with a mass of 12 AMU, versus about 1% of the time you would find a carbon 13 isotope that has a mass about 13. So that's what the percent abundance, it's sometimes called relative abundance, percent abundance. It's basically the percentage at which that isotope is found in nature compared to the others, so it's not like a 50-50 split. Like if you have 2, you're always going to find like, kind of like a 50-50 of the time. Again, some occur a lot more frequently in nature than the others, and that's what the percent abundance basically means. Yeah. Like in this case here, this one is a kind of a 50-50 split on this particular example here. So basically what those percentages say in this case of the bromine is, 50% of the time you probably have a good chance of finding the 79 isotope, right, with a mass number of 79. And about almost 50% of the time you would find the one maybe with the mass number of 81. So that's sort of the percentage is what they mean. Other questions? All right, let's try one more here just for fun, I suppose. An isotope that was 70.5% abundant with an atomic mass of 117.8, while the other isotope has an abundance of 29.5% with an atomic mass of 120.85. Calculate the atomic mass of this element or whatever it may be. Okay, let's take a look. So again here, we're not really sure what it is, but we do have a couple of isotopes information given to us. Once again, just going to take a quick look at the percentages. We are close to 100, so we're really not missing any isotope in this case. So we could use our formula there, our atomic mass. And again here, we're going to take our first isotope, and you could either move the decimal like I mentioned, or you can, again, divide by 100, which will do it for you. Then you can times that by the atomic mass of our first guy, 117.80 AMU. We'll add it to our second isotope. Once again, you can move the decimal or divide by 100, and I'll just move the decimal on this one, and we'll times it by 120.85 AMU. And if we put all that together, once again here, I would probably use equals in between and then open a parenthesis for the second part of that calculation. And that's going to get us about 118.7 AMU in this particular case as the atomic mass of this particular element. Yes, sir. It is. So it's really your preference, whichever way you want to do it. If you need to always convert a decimal into sort of I'm sorry, a percentage into a usable one, just move the decimal 2 places to the left, and that basically is divided by 100 is what they're doing there. Now, as to maybe the earlier question, we can use this information if maybe we ran the sample right through our machine and we weren't really sure what we were dealing with. We now know that this thing has an atomic mass of about 118.7, which means what element would I be dealing with? It would be tin, right? So again, this is sort of like the question of sort of a practical application. If you had something you weren't really sure what it was, you could run it through this sort of analysis and maybe know what at least what elements, right, are involved if it was something that's pure. Any questions on that there? Okay. All right. So what is the relationship between an atomic mass unit and grams? That is the relationship there. I don't know how often you'll actually use that conversion per se, to be truthfully honest with you, but in case you need it, there it is right there. 1 AMU is 1.66 times 10 to the minus 24 grams. And one of the ways we can use atomic mass from the periodic table is to figure out in AMU, the mass of so many atoms. And I will say we'll go through these calculations, but probably practically speaking, um, you probably will never do these calculations in chemistry, these few here. The previous one, yes, maybe, but very often we're not really interested in AMU as a unit, right? You go to the balance, you don't really getting it in AMU, right? You're getting it in grams, which is a more usable sort of unit. So you can use this relationship that you get from the periodic table as a conversion factor. And like I said, pretty much any one that you take off of the periodic table, you can take that bottom number there. And again, use it really as a conversion factor. And again, it means it has 12.01 AMU per atom. And because you could use it as a conversion factor and do a little dimensional analysis, you could flip it around just like any other conversion factor and kind of use it in the opposite direction if you needed to. So in the case of this particular question, we're interested in how much the mass in AMU is of 431 atoms of carbon. So obviously we would take our 431 grams, our carbon atoms, we would set up dimensional analysis, and again, just going opposites cancel like we talked about. Atoms on top means atoms need to be on the bottom, would give us an atomic mass for those guys of 5176 AMU, which again, to most people are, I don't want to say a useless unit because again, we don't think of mass in terms of AMU and stuff like that. But you could figure it out in terms of that. Same thing here with aluminum. If you went and looked on the periodic table there underneath aluminum, you would see 26.98. And once again, four significant figures, 2698 AMU per atom. Or again, if you needed to, you could flip it around and use it in the reverse direction. And again, we would set it up again, dimensional analysis here, atoms on top, so atoms cancel on the bottom, gets us 2024. A reminder that we are, again, multiplying the top and dividing, right, what's on the bottom, just like we talked about, obviously, at the beginning there with dimensional analysis. So, as I mentioned before, the AMU unit is obviously a legitimate unit. It is not used a lot in sort of real life practication because again, we're more interested in grams. So this brings us to really I would say, a conversion that you use a lot in chemistry. So unlike the last one where you might not use it all that much, this one definitely you use a lot. And that's molar mass, which is probably the calculation in chemistry that you use the most, and Avogadro's number, which is a nice number, and we do use it, but not as much as molar mass. So I would say out of these two, for sure, molar mass is a calculation you should definitely master, as that is something we use in all calculations, or a lot of calculations uses the molar mass. Avogadro's number is also a really important sort of conversion that's used to go from one type of unit to the next. So let's talk a little bit about each of these. So first off, we're going to talk about the mole. And the mole is a unit in chemistry that does represent a certain amount of something. So in life, we have a lot of words that we use to represent a certain amount of something. If you have a pair of something, right, that means you have two. If you give somebody a dozen roses, you gave them 12, right? Or you got a dozen donuts, you got 12. If you did like a gross of pencils, which they don't do too much anymore, that's 144. So there's a lot of words that we have in life that actually does represent sort of a numerical value. And in chemistry, that word is the mole. And the mole represents a certain amount of something. The mole is abbreviated as MOL. And again, I think we might have touched upon it a little bit earlier on, but that is the actual abbreviation for a mole. And I say that because a lot of people, when they see the MOL, their mind automatically goes to molecules. So they think like molecules when they see that. And that is not the case. So it is the abbreviation for mole. I would say in chemistry, if they are interested in molecules, they will actually write out the word molecules. So they'll actually write out that word. So when you see that MOL, it is moles. And it represents the same amount of elementary entities there are in exactly 12 grams of the carbon-12 isotope, which was our standard that we used for our atomic mass that we just talked about. So what is the deal with a mole? 1 mole of anything represents this amount, which is 6.022 times 10 to the 23. That number of 6.022 times 10 to the 23 is really the numerical representation of a mole. Now, as we will talk about, the units associated with this number can change. So in certain cases, this could be particles. In certain cases, this number could be atoms. In other cases, they could be molecules. It could be pizzas, if you're talking about pizzas, or shoes, or whatever you want to be. So this 6.022 number times 10 to the 23, the units of that changes, but it represents 1 mole of something. Just like when you tell somebody you have a dozen donuts, you have 12. And when you say you have a mole of something, you have 6.022 times 10 to the 23. Any questions on that there? That number does have a specific name, and that number represents what is known as Avogadro's number. So when somebody says Avogadro's number, this is the number. The rounded version is typically what people use, the 6.022 times 10 to the 23. Now, Avogadro's number is really used as a conversion factor, and that's how you should think of it, as a conversion factor. It is the conversion factor that allows you to go from moles to atoms or molecules, which I would say is probably the top 2 ways that you would calculate. You don't run across too many problems in chemistry where you're calculating how many pizzas you have, but molecules and atoms are typically the common sort of units that you use. But again, it really can't be anything else. And it also allows you to go backwards if you are starting with atoms or molecules. Avogadro's number is the thing that will allow you to convert back into moles. So you could use it as a conversion factor as 6.022 times 10 to the 23. And again, you can use atoms or molecules over 1 mole of something. Or you could put the mole up on top, and that would equal 6.022 times 10 to the 23 atoms. So it really is like a conversion factor, and that is what it allows you to do. And go between those 2 units, again, doing dimensional analysis, and opposites cancel. Now, should you use Avogadros in every situation? And that is also a problem a lot of people have, is they learn Avogadro's number and feel like they should use it like in every calculation they ever do. And that is also a big mistake. You should not do that. So the only time you should pull out Avogadro's number is one of two situations. Either you are asked to find atoms of something or molecules or particles, something like that, or you have a number in front of you that's in atoms or molecules or something like that. If there is no mention of atoms or molecules or anything like that, you probably should leave Avogadro's number on the sideline. And that's a very common mistake. Sometimes people mess up okay in the sense that they will for sometimes divide by Avogadro's number in the beginning and then multiply at the end, so they kind of cancels each other out. But you definitely don't want to use it in every calculation. Those are the key words you want to look for: atoms, molecules. Either you're trying to find one of those or it's given to you, and that means that somewhere along the way you need to use that. The other important thing is, obviously, like we talked about at the beginning, you need to make sure you definitely use your exponent button, right, when you put this into your calculator. So make sure you punch it in just like a number, obviously, in scientific notation, and you want to punch it in. Clearly, obviously, here you need to know it, so you do need to know Avogadro's number. It will not be provided for you, so you do need to be able to do that. So that is a conversion factor that takes you from moles to atoms, atoms to moles. And you could use the relationship, for example, from the periodic table. What is the difference between using atoms or molecules, or why you would want to use atoms, say, versus molecules? Let's just say you had lithium. And if you go to the periodic table and you look at lithium, underneath lithium, 6.941, if it had a true number there. And when we look at lithium, what we could say is, in this case, if I have 1 mole of lithium, it would have how many atoms of lithium? It would have Avogadro's worth of atoms, 6.022 times 10 to the 23 atoms of lithium. And again, that is the relationship that you could get from anybody on the periodic table. That again is going to give you your two possible conversion factors that you could use in a problem if you needed to. Or again, obviously you could flip it around the other way and put the 6.022 times 10 to the 23 up on top over a mole of lithium. Now, let's just say you're not just talking about lithium, but maybe you're talking about water, right? Water is not an element by itself, right? It is a compound, it is a molecule. And if we wanted to know, for example, how many molecules there are in 1 mole of water, how many molecules would there be in 1 mole of water? It would still be Avogadro's number. So it would still be 6.022 times 10 to the 23. The difference though here, water is a molecule. So instead of atoms on that, we would use molecules. So that's what I was saying earlier. That kind of number will have some units that might change, but the number is going to be the same. This also will give you your two conversion factors you could use. 1 mole of water is 6.022 times 10 to the 23 molecules. Or you could pop that guy up on top, 6.022 times 10 to the 23 molecules is 1 mole of water. So, for example, if you're doing something that's kind of a compound, a molecule, you typically would use Avogadro's number with the molecule sort of units. If you're doing just like an element from the periodic table by itself, you would use more atoms as sort of the unit that goes with Avogadro's number. Any questions on that there? Yeah. So is it when you add molecule or Avogadro's? Those are the keywords you want to think about. Yeah. So if you come across a problem, like I said, that it's mentioned somewhere, either they want you to find one of those units or you actually have a number in front of you that is in one of those units. What that usually means is if you are given a number that's in those units or you're trying to find it, somewhere along the way in that calculation, you're going to have to use Avogadro's number, either to go from moles to atoms or molecules, or to go from atoms to molecules kind of back to moles, and you'll have to use it. Yeah. Other questions? So again, as I mentioned, the term mole does represent a certain amount of something. Just like, again, if you had a dozen oranges, you would have 12. If you have a mole of anything, it's always Avogadro's number. And again, you adjust kind of the units of that number based on what you're dealing with. Now, as I mentioned earlier, when we were talking about AMU in terms of atomic mass from the periodic table, that again is not really the unit that we use a lot because it's not a usable sort of unit in a lot of cases. So that brings us to probably the most common conversion unit that you will use here, which is molar mass. And molar mass is the mass in grams or kilograms, but most of the time it's in grams of 1 mole of a unit of a substance. So, where do we find molar mass? Well, we find molar mass in the exact same location of where we find atomic mass. So, that number on the bottom of the periodic table is also commonly referred to as the molar mass of a substance, in addition to the atomic mass. We oftentimes use it from the periodic table as the molar mass because, again, it involves a unit that's more usable for us. And just like atomic mass, if you need to go to the periodic table, typically speaking, commonly 4 significant figures is what you want to kind of, again, pull off of the periodic table. What are the units of molar mass? The units of molar mass are grams per mole. Both of those units together. The number that you calculate always stays with the grams part, and it's always per 1 mole. So when you calculate the molar mass of something, you're calculating it per 1 mole of that guy, which is basically just the formula. So if you just took the formula by itself of whatever you're dealing with, one of those formulas is what you're calculating how many grams there are. Now, it is really a conversion factor, and it is used to go from grams to moles or moles back to grams. That is your molar mass conversion from the periodic table is where you grab that from. And you could grab it from the periodic table. So basically, if you look at hydrogen, basically that means that there is 1.008 grams of hydrogen in every 1 mole of hydrogen. That gives you your 2 conversion factors that you could use. 1.008 grams of hydrogen per mole. Or again, you could flip it and use it as moles up on top, 1.008 grams on the bottom. It again, in a way you should really probably think of molar mass is it's really just a conversion factor. And where you get that conversion factor from is the periodic table to do so. How would we use it in a calculation? Just like any other dimensional analysis. So for example, if I had 32 grams of hydrogen and I want to know how many moles that was, I would use the molar mass. Again, just like dimensional analysis, grams are on top. So to get rid of it, I need grams on the bottom. I would go moles of hydrogen up on top, 1.008 grams of hydrogen on the bottom. The grams of hydrogen are going to cancel. We're going to multiply and then divide there. And grab my calculator here. We'll go 32 divided by 1.008. Going to get me 31.7 moles of hydrogen in this case. By the way, this would be considered an exact number, so significant figures right there is probably where you should look, which would be 3 significant figures in this particular case. Now, you may be saying to yourself, isn't that the AMU for hydrogen? And you are right. Numerically speaking, if you do the conversion between the units we saw earlier, AMU per atom, to grams per mole, they end up being numerically the exact same number. So the exact same number that you would have for the atomic mass in AMU per atom is the exact same molar mass you would have grams per mole. So when we look at sodium, 2299 AMU per atom, sodium's molar mass is 22.99 grams per mole. Copper's atomic mass is 63.55 AMU per atom, its molar mass is also 63.55 grams per mole. Again, we use molar mass more because, again, it gives us that gram unit, which is much more useful in sort of practical application in terms of our calculation, but they are numerically the same. And it has to do with that conversion we saw earlier between the AMU in grams and the Avogadro's number conversion as well. And when you do that conversion, they end up being the exact same value. Yeah. Say again. Oh, I'm sorry. Yeah. So the mm here stands. That's the molar mass you want to use as a conversion factor. The PT is you get it from the periodic table. Yeah. So that's where you can find it from. It's on the periodic table. So whenever you think molar, where to find it? Yeah. It's a No, it's not. I was just put PT like, hey, that's where you go find it. So sometimes people are like, where do I get the molar mass from? It's from the periodic table. Basically, the number on the bottom. That's where you could go find that kind of conversion to do so. I just made that number up. Yeah, as an example of how to use it. Yeah, and then obviously this came from the periodic table as the number underneath hydrogen in this case. That's correct. Yeah. Now we did this for hydrogen. And we talked about we could use hydrogen and Avogadro's number for atoms. And we also talked about that we could use like water and molecules. We could also do the molar mass for things that are not just elements. So for example, if we had water and we wanted the molar mass of water, we basically would just add up all the parts. So again, we would go to the periodic table and we would find hydrogen. And there's not just one hydrogen there, right? There are two. So we would do 2 times the molar mass of hydrogen, which is 1.008 grams per mole. We would then add it to the molar mass of oxygen. So again, if you go to the periodic table, you will see underneath oxygen 16 written. And that is 16 grams per mole, which is the molar mass of oxygen. So this takes care of our hydrogens. And this is the oxygen that is present there. And if we add all that together, we get this number, 18.02 grams per mole. That is technically the molar mass of water. It also can be used as a conversion factor, just like we did with the hydrogen or the other one. We could say that there are 18.02 grams per mole of water, or in a mole of water, there is 18.02 grams. So you can use it either way. And again, dimensional analysis is a good way to kind of do your calculations we've been talking about. Again, you just got to go opposites to get rid of what you don't want. Question on that there. Now, as you can see, the number stays with the grams part and it's always per 1 mole. I will say this now, and it may not make sense, but hopefully it'll make sense a little bit later. And this is also a very common error that people make. So for example, we've all seen equations, right? I think we looked at some as we were doing chapter 10 when we kind of went out of order. But if you looked at an equation, let's just say you had 3 waters in your equation, and it's a balanced equation, and you have 3 in front of it. And at some point in this calculation that you may be doing, you need the molar mass of water. A super common error that people make is they see the 3 here and they think, okay, I need to kind of not do that, but I need to move that down. I need to multiply this by 3, and you should never ever do that. So whenever you are calculating molar mass, the units of molar mass are grams per 1 mole. And what that means essentially is regardless of whatever coefficient there may be in an equation, and if you need the molar mass of that substance, all you should do is just take the formula by itself, add up the parts. It doesn't matter if there's like a 40 in front of it in the equation or anything like that. If you need the molar mass of water, you should just take the H2O, and that is what you should use to calculate the molar mass of it. What do you use the coefficient for? We'll talk about it in about 2 chapters, but you use the coefficient for some other part of the calculation, but never molar mass. So molar mass should always just be based on the formula, add up all the parts. Any questions on that there? Now, what is the sort of relationship between all those things? So for example, if I have 1 mole of lithium, I know from the periodic table that That is 6.941 grams of lithium. And I also know that if I have 1 mole of lithium, that is 6.022 times 10 to the 23 atoms of lithium. All those things are related to each other. Yeah. Just like I know if I have 1 mole of water, I have 18.02 grams of water in that 1 mole, and I know I have 6.022 times 10 to the 23 molecules of water in that mole. So that's the relationship between all of them. Again, I would say most of the time and probably in most of your calculations, it is going to be probably a grams to mole molar mass situation. Every so often, though, you do maybe need molecules or you have something in molecules or atoms, so you do need to throw Avogadro's number in there. But probably more times than not, it's going to be a molar mass calculation than, let's say, an Avogadro's number, but it does pop in Avogadro's number along the way as well. Any questions on that relationship there? All right. And that's just how we get to that number we saw earlier. It's not all that important for us here, I think. And again, that's how we get there. So you probably rarely ever use part of these conversions, so you don't have to worry too much about it. So what is the deal with Avogadro's number and molar mass? It allows us, as I've been mentioning, to do those conversions. So once again, Avogadro's number takes you from atoms or molecules to moles or backwards. And molar mass from the periodic table takes you from grams to moles and moles back to grams. As I mentioned before, pretty much most calculations you do in chemistry, a lot of them start with taking grams and converting them to moles. So using that molar mass is almost like a lot of cases the beginning part of the calculation for a lot of different calculations that you do in chemistry. Any questions on that there? All right, why don't we try one here? How many moles of helium are there in 5.46 grams of, there are in 5.46 grams of helium? So the first question is, do I need Avogadro's number here? I do not, right? Again, a reminder that when you see MOL or moles, it is different than molecules. There is no mention of molecules. There's no mention of atoms. You're not looking to find any of those units. So we do not need Avogadro's number. This is basically a conversion between grams to moles. And again, as we've been talking about, that is your molar mass. Once again, from the periodic table is where you're going to get that from. So you would go to the periodic table, you would find helium, and that's essentially what you would see underneath it. Remember that we can pull this number off of the periodic table, and that's really where we're going to get our conversion factor to use. This would mean the molar mass of helium is 4.0003 grams per mole, and that really is the molar mass of helium. Again, we could use it like a conversion factor, and if we needed to, we could also just flip it around. By the way, though, if you are asked a question of what is the molar mass of helium, this would be the right way to enter it in, how many grams there are per mole, not moles per gram. So grams per mole is really the true units of molar mass, but we do use it as a conversion factor, which means you could flip it. So if you are just asked a question of what is the molar mass, you would want to give it like the guy on the left there as sort of the answer. In this case, we want to just take a dimensional analysis approach. So 5.46 grams of helium. Remember, it's not written as a fraction, but we can see that grams are on top. And again, because we have our two options here, we could just go opposites cancel. So it takes all the guesswork out of it, right? As we talked about, that would be the one I boxed there, the one that you would want to use on the conversion here. Again, we would set it up just as dimensional analysis, moles on top, and 4.003 grams of helium on the bottom. Again, we're going to multiply and then divide. The grams of helium will cancel. It's going to leave us moles, which is what we're looking for in this case. And we're going to get 5.46 divided by 4.003. Going to get us a 1.36 moles of helium would be our answer. Once again, this is an exact number, so in this situation, you would look back on the original number here, which has 3 significant figures, And that is probably what you would want to use. Any questions on that one there? Let's see here. How about this one? What is the mass in grams of one gold atom? In case you can't see the periodic tables in this room. Gold there on the periodic table, 197. All right, so take a few minutes there, set it up. We're looking for the mass in grams of one single gold atom in this case. Okay, so let's see how you're doing. So first off, we want to know, do I need Avogadro's number in this problem? I do, and again, the keyword here to tell me that somewhere along the way I do need to use Avogadro's number is I am actually given atoms to begin with. So I definitely need to use it. We are starting with atoms. We eventually want to get to grams. And remember that the unit that sort of ties both of those guys together are moles, right? So that is sort of the unit that kind of ties both of those sort of end units there together. So I know that if I'm going from atoms to moles, that is definitely Avogadro's number territory in terms of conversion. And once I have it in moles to go from moles to grams, that is now molar mass, right, from our periodic table that's going to allow me to kind of do the end result of it. So I do know that 1 mole of gold in this case would equal 6.022 times 10 to the 23 atoms. I also know from the molar mass from the periodic table that 1 mole of gold will equal 197 grams here gold. So again, we're going to start with what was given, which is one gold atom. So we're going to use Avogadro's number up front here. Remember, just take it dimensional analysis way and just got to go opposites. So atoms are on top, which means I do need atoms on the bottom here. And here we are using atoms because obviously we're just talking about gold by itself there, and it's not a molecule or anything like that per mole of gold. If I stop the calculation right at this point, the atom units have now canceled each other out. I am left with moles, which if you wanted to, you could get a number, but as we talked about previously, just try not to round too much, right, until kind of the end. Here, I'm just going to kind of continue on with my calculations. So I just basically got to here, right, by using Avogadro's number. Now I need to go the rest of the way by using the molar mass. Again, by setting this thing up in dimensional analysis, it is very clear to me that the moles of gold are up on top. So again, opposites to cancel means I need to put the moles of gold on the bottom, and up on top would go the 197 grams. The moles again will cancel, and the only unit left standing at this point are grams, which is what we're looking for. Once again, since it's dimensional analysis, all we are doing is multiplying and then dividing, right? So we'll come through here and do that. Essentially, up on top, we basically just got 197. You can multiply it by 1, but nothing much is going to change there. We're going to divide it by Avogadro's number, making sure to use our exponent button. And that would get us 3.271 times 10 to the minus 22 grams of gold, which is a very small number, which you would expect it to be since it is one single gold atom in this case. First off, any questions on that there? Now, in terms of significant figures, really, this is sort of exact. This is exact. Although it is an atom, typically speaking, and it would be something you probably would count, right? And be kind of an exact number. So you really could have went probably as many significant figures as you wanted on this one. I went 4, I think, for the molar mass, and so that should be sufficient in this case. Any questions on any of that calculation there? Yeah. All right, so let's try another one here. We got zinc. How many grams of zinc are there in 0.24, 0.256 moles of zinc? Zinc is It changed it over the years. 6530. So let's take a look at this one. First off, do I need Avogadro's number on this one? The answer is no, because remember, this is moles and not molecules. Yeah. So again, that's a very, very common mistake. People again see that MOL and just automatically think molecules. This is really just moles, and I want grams, so it's really just this conversion going from moles to grams. Again, a reminder, that is the molar mass from the periodic table that's going to allow you to do that. Here we would go there to zinc and get our conversion factor. That's 6538 grams equals 1 mole of zinc. And again, we're going to use that just as a conversion factor. We'll start with what was given to us, 0.256 moles of zinc. Once again, it is up on top the moles. So opposites cancel. That means I need to go a mole of zinc that I got from the periodic table represents 65.38 grams of zinc. When we multiply and then divide, our moles will cancel. And that's going to end up here 0.256 times 6538, about 16.7 grams of zinc in this case. Again, significant figure wise, I'm not going to really look here, so I'm going to come back to this number here, and that's going to be 3 significant figures, so that would be what I would go with in this case. Any questions on that one there? So again, you really want to think of molar mass, and even Avogadro's number really is just conversion factors, right? And again, where we get the conversion factor for molar mass is from the periodic table, and obviously Avogadro's number is just always that number, so that is always sort of a one that you have. All right, why don't you try a couple of these here? How many moles are there in 23.2 grams of ethanol? And also, how many molecules are there in the 23.2 grams of ethanol? Let me give you some numbers that might be helpful. 12.01 for carbon, hydrogen 1.008 from the periodic table, and oxygen about 16 there. All right, let's take a few moments there and calculate each of those there and see what you come up with. Okay, so let's take a look. So in the first one here, we want to know how many moles are there in 23.2 grams of ethanol. So for the first part of the calculation, it just basically we want moles and we have grams. So again, that is our grams to mole conversion, which is the molar mass there from the periodic table that's going to allow us to do that. We do need to just basically add up all the parts here, right? So there are in the formula here 2 carbons, so we will take 2 times the molar mass of carbon from the periodic table. That'll take care of our carbon part. We'll add it to our 6 hydrogens there are, so 6 times the molar mass of hydrogen from the periodic table. Again, that's going to take care of the hydrogen part. And we just got 1 oxygen, which is 16 from the periodic table. And again, just going to basically add up all the parts from the formula there. And that's going to get us here 2 times 12.01 plus 6 times 1.008 plus the 16. Looks like 46.07 grams per mole would be the molar mass here of ethanol. First off, any question on how we got that number there? It wouldn't be because again, just in general, even in a situation like this, you would want to go to 4 significant figures. Yeah, and technically speaking, the 16 on most periodic tables is 16.00, which would be still 4 significant figures. And really, in this case, you're adding, so you would want to go to kind of decimal places, and 2 would be the smallest. But just in general, just 4 is usually the pretty safe bet on that. Yeah. Other questions? That again is going to be our conversion factor to do our grams per mole. So we really have everything we need to do the first part here. So we'll go 23.2 grams of C2H6O. Again, just going to take the dimensional analysis approach. Grams on top means for sure grams need to go in the opposite location, which is on the bottom in this case. Again, the grams are going to cancel. We're multiplying and then dividing in this case. So we're going to take 23.2 divided by 46.07. And that's going to get us here 0.504 moles of C2H6O in this case. Again, the three sig figs off of the 23.2 number that we started with. First off, any question on that there? Really, the second part here is just a continuation of this problem, right? We actually have it in moles at this point. We want to really go from moles to molecules. And that is the key word there, right? Molecules. So that tells us now we're into Avogadro's number territory. That's going to allow us to do that. Again, 1 mole of ethanol would equal 6.022 times 10 to the 23. These would then become molecules here since we're talking about ethanol instead of atoms. And again, that's just going to be our conversion factor to kind of take it the rest of the way. I personally am, since I still have the number in my calculator, I'm just going to continue on with the actual number I have in my calculator. The unrounded number, since I want to kind of continue on again, maybe avoid some rounding errors or something like that. We're going to go opposites here. So moles are up on top. That means moles need to go on the bottom, opposite location. Up on top is going to be our Avogadro's number. The moles will cancel. Again, we're going to multiply here. And again, I'm using the entire number there, not the rounded number, 0.5035815. 6.022 exponent 23. And that is going to get us here 3.03 times 10 to the 23 molecules in this case. Again, using the sort of unrounded number there. If you used a rounded number, you probably should get something fairly close. I think you may have 3.04, bless you, 3.04. I said a 3.03, which would be okay as well. Yep. Any questions on that one there? Okay. So let's take a look at, why don't you do this last one here and then we'll take a look at something, I think. So we got carbon, again, 12.01. We got hydrogen, 1.008. Let's take a look at this one. Again, we have one molecule here. We want to get to grams. So again, we're going to start with molecules, which does tell us Avogadro's number should be involved. We want to get to grams. And as we saw in that previous one, again, it is the moles that kind of ties both of those together. So we will need to go similar path here, Avogadro's number to get us some moles. And then to take us really the rest of the way here, we do need from the periodic table our molar mass sort of conversion. So we do know that 1 mole of this guy here, biggest formula ever, is 6.022 times 10 to the 23 molecules. We do need the molar mass, so might as well calculate that while we're here. Again, we're just going to add up all the parts here. So we do have 8 carbons, each at 12.01. Again, that takes care of the carbons. We do have 10 hydrogens at 1.008 grams per mole. It's going to take care of our hydrogens. We're then going to add it to 4 times our 14.01 for our nitrogens. And lastly, 2 times 16 here for our oxygens. And if we add all that together, we're going to end up with something times 12.01 plus 10 times 1.008 plus 4 times 1401, and that's 32 basically. So looks like 194.2 grams per mole, I think. Sure, I punched that in right. times 1.08 plus 4 times 14. All right, so that is our conversion factor at the end. We're going to start with our Avogadro's conversion factor. So once again, here we have 1 molecule of our caffeine. We're going to go opposites to cancel. So Avogadro's number is going to go on the bottom here. And 10 to 23 molecules per mole. That's going to get us basically to our center step here, where our molecules are going to cancel. We can see moles are on top. So again, molar mass to go the rest of the way here. Since moles are on top, moles need to go on the bottom to cancel. And 194, let's say there, 0.2, I think. 0.2 grams up on top. The moles are going to cancel, going to leave us grams. Again, multiplying what's on top, dividing what's on the bottom. Right? So that's going to get us here, basically 194.2 divided by Avogadro's number, I think, in this case. And that'll get us again 3.225 times 10 to the minus 22 grams here of our caffeine. Questions on that bit. Question on grams to moles, moles to grams, which again, use a lot. Avogadro's number. All right, one more thing to talk about here that does come about. So why don't we maybe just still this guy. So let's say, for example, we have this problem here, and so somewhere right. And let's say that instead of the questions that were asked here, we are interested in, if we started with our 23.2 grams of ethanol, maybe we want to know how many moles of hydrogen would there be? And we're just interested in just the hydrogen, not the entire thing, but just the actual hydrogen. And in a situation like this, where you may not be interested in the whole entire thing, but maybe you are just interested in an element that's part of the compound, you can actually use the formula itself as a conversion factor. And when you look at a formula and you look at these subscripts that are here, and obviously in the case of oxygen, it's a 1, these do represent the moles of each of those elements that are here. So from the actual formula itself, you could actually come up with a number of conversion factors. So for example, we could say that in 1 mole of ethanol, we actually will have 2 moles of carbon. And again, that comes from the subscript from the actual formula itself. We could also say in 1 mole of the entire thing, there would be how many moles of hydrogen in this case? There would be 6. Yeah, so again, the little subscript there, 6 moles of hydrogen. And we could also say for every 1 mole of the entire thing, there would be 1 mole of oxygen. So we actually come up with 3 kind of conversions that we could use. We obviously could write 2 conversion factors for each of these equalities. And what this is going to allow us to do is use the formula itself to go from the whole thing to just the element we're interested in. So before we could use this, though, right, these are all essentially mole-to-mole relationships, right? So we would need to get our units into moles of the entire thing. And we happen to have done that here in the first step. So I'm just going to kind of steal this so we don't go backwards. But if we were starting with 23.2 grams of ethanol and want to know how many moles of hydrogen that would be, we would do the first step exactly what we did here. We would take the whole thing and convert it from grams and then convert it into moles. At this point, I now have moles of my whole thing. And now I can use the actual formula itself as a conversion factor. So I want hydrogen. So in this case, I would use this equality here as my conversion factor. Again, going opposites, so moles of the entire thing would go on the bottom. And in this case, 6 moles of hydrogen would go up on top. And that's going to allow me to go from the whole thing to just the hydrogen part. The moles of the whole thing would cancel, and I would end up with 0.504 times 6 in this case. And that would get me something like 3.02 moles of hydrogen. What happens if I want to know how many grams of hydrogen that would represent? What should I use next? I would need what to go from moles to grams? The molar mass from the periodic table of hydrogen in this case, right? So if I want to know how many grams that would represent, I could go back to the periodic table, use the molar mass of just hydrogen in this case, and the moles of hydrogen would cancel, and you would find out that that would represent that there are, we'll call it 3.05 grams of hydrogen in that 23.2 grams. So out of that 23.2 grams, basically 3 grams of it is hydrogen, right? This particular case. Any questions on that? Yeah. That's what these little numbers on the bottom represent. They actually represent the moles of each of those elements that are present. So you could use it as like a conversion factor in that formula. You're basically saying you have 2 moles of carbon, 6 moles of hydrogen, and 1 mole of oxygen come together. And that's what these, again, little numbers on the bottom, that is what they represent. And since they represent the moles of each of those things, you can use it as a conversion factor. Because basically what you're saying is in 1 mole of this entire thing, so if we took this entire thing, there's basically 2 moles of carbon present, there's 6 moles of hydrogen, and there's 1 mole of oxygen present. So it's just a relationship that you can use from the actual formula to get the mole to mole relationship. Exactly. Yeah. So exactly. For in this case, the question I made up was how many moles of hydrogen. But if we were interested in carbon, for example, in this case, we could have started with this again. And instead of using obviously hydrogen's relationship, we would have used the carbon relationship in this case. And if we were interested in carbon, we would use basically this relationship here that we got from the actual formula itself. And we would do the kind of same thing, 1 mole, the whole thing on the bottom, so it cancels, and 2 moles of carbon up on top. And that would tell us in this case how many moles of carbon there would be present. And if we want to know how many grams of carbon that would represent, we could also do that as well. And so in this case, we would get something like about 1.008 moles of carbon. And we could use the molar mass for the periodic table, carbon 12.01 grams per mole, as I squeeze it in here. And we'll end up with about 12.1 grams of carbon was present in that particular guy. And believe it or not, if you add that up along with the 3 grams, you'll know that there's 23 grams we started with, right? So the rest of that mass is going to be the mass of the oxygen atoms that are present in this case. Which you could do the same calculation for oxygen as well. Other question on that? Yeah. They are not the same thing. Yeah. And that is a super common error that people make. Like I was saying earlier, when people see this abbreviation for moles, they automatically think molecules because it kind of looks like it would be logically the abbreviation for molecules, but it is the abbreviation for moles. They had to cut something out, so they cut the E out. But it's a super, super common error that people make that when they see that, they go molecules. That's why I said earlier, I would say in chemistry for the most part, if they want you to do something with molecules, they will actually write out the word molecules. It's they definitely won't abbreviate, and it's really for this reason. Most cases they won't abbreviate it because then you don't know if you're dealing with moles or molecules. So the kind of general rule is typically if it has something to do with molecules and they want molecules, they will write out the word molecules. But if you see MOL, it definitely is always the abbreviation for moles. Other questions? All right, so that's just a little common type question that sometimes you come across where maybe you're not interested in the whole thing, but you are interested in maybe one of the elements that are part of a compound and can use the actual formula itself as a conversion factor. Questions on any of that? Now that we talked about that, let's then talk about how we get to those formulas. And we'll talk about two different types of formulas that we're going to talk about. The first type of formula, which is really important, is a molecular formula. And obviously, we talked about the idea of molecules as a basic definition of all you need for something to be a molecule is two or more atoms together. It can be two or more of the same element or different elements. Remember that if it is a compound, it does has to be different elements coming together. A chemical formula expresses the amount of each of those elements that are present in it. And the molecular formula is really the formula that tells you exactly what is present. So when you see a molecular formula, it tells you exactly, for example, how many carbons are present, how many hydrogens are present, how many oxygens are present. The simplest molecular formulas we have are actually those diatomic molecules we talked about, right? So when you see H2, O2, N2, again, this 2 tells us there's two hydrogens together, there's two oxygens together, there's two nitrogens basically together in this case. In their simplest form, molecular formulas are written by grouping atoms of the same element together. And sometimes molecular formulas, although they do tell you exactly what is present, sometimes they don't necessarily give you a lot of information about how things are attached. And sometimes people get confused because sometimes people will use a molecular formula and it's just the basics of these are the elements there and how many of each one. Now, sometimes people will write molecular formulas that give you a little bit more information. So probably one of the commonly seen ones that people run across is something like this. And for example, that is really the same thing as what we got almost going there on the bottom, but we'll go here. We got H4O2. Now, these are both molecular formulas. These are both actually molecular formulas for the same thing. This is both acetic acid, which is basically the main component of vinegar. And although one gives you a little bit different information than the other, they both basically tell you there are two total carbons, right? Two there, one carbon and one carbon. So two carbons there. Yeah. You will not. Yeah. So here there are four hydrogens. There are three hydrogens there, and one more is four. There are two oxygens there, one oxygen, two oxygen. So what is the difference, and why do people sometimes write molecular formulas one way versus the other? The one on the left is just a basic molecular formula that really just tells you what's present. The one on the right actually gives you some information about how everybody is attached to one another. If you were to draw the guy on the right, it would look something like this. And you can see there's CH3, CH3, CO, CO, OH, OH. So the guy on the right gives you a little bit more structural information about how it's put together. But they are both legitimate formulas, and you can use both, and they are used interchangeably a lot. And so sometimes when you do see formulas, for example, this happens a lot in labs. So in labs, sometimes they'll write the instructions and the procedures with a certain formula, maybe the guy on the right. And sometimes the labels on the bottles, because they don't have a lot of room sometimes, they'll just use like the formula there on the left. And sometimes people can never find the reagent they're looking for or the chemical they're looking for because they're looking for CH3COOH, while on the bottle it just says C2H4O2. So it's a very common thing that you'll come across probably as you continue your lab career here. Very commonly, that sometimes happens that, they use different types of, yeah. Honestly, truthfully, if you were asked to write the molecular formula, either one is perfectly fine. I personally, just over the years, for this particular example here of acetic acid, I personally roll with this one. But a lot of people will kind of roll with that one as well. And it does create some issues. I've been in a lot of labs I've taught where people are like, where did I find this thing? It's sitting right in front of them. But because they wrote the molecular formula kind of differently, they don't realize it's actually the same thing. So sometimes that does happen a lot, in the lab and stuff. But they're both perfectly fine. You can kind of do either one. Other questions? All right. So, but the key though here is the molecular formula does tell you exactly like that is what's in there. That is exactly how many of each of these elements are in there. Now, the empirical formula, which is another type of formula, is the simplest whole number ratio of what's present. It does not necessarily tell you exactly how many of each of those elements are in the actual formula or the compound. It is the simple ratio of what is present. So, for example, if you took hydrogen peroxide, like in this example, we know that there are 2 hydrogens for every 2 oxygens present. That is basically a 2-to-2 ratio, which you could reduce down to a 1-to-1 ratio, right? If you divide both 2's by 2, you get 1-to-1. And that would give you an empirical formula of HO. This would be the simplest representation of what is present. Now, empirical formulas are the simplest representation. So if you had C2H6 as your molecular formula, and you wanted the empirical formula, this tells you there are 2 carbons for every 6 hydrogens that are present. That is basically a 2-to-6 ratio. Can you reduce down 2 and 6? Divide everybody by 2. And you will get a 1-to-3 relationship, right? And that basically means that our empirical formula would be CH3, would be the empirical formula. By the way, the numbers on the bottom do need to be whole numbers. You cannot have like a half an atom of something, right? So they have to be whole numbers. With that being said, if this is our molecular formula here for water, what would be the empirical formula for water? Can you reduce that down anymore? You have, in this case, 2 hydrogens for every 1 oxygen. That's basically a 2-to-1 relationship. Can you reduce that down and still get a whole number for everybody? You cannot. So H2O is both the molecular formula and it's also the empirical formula, right? And sometimes they are the same formula for a compound. So for water, the empirical formula and the molecular formula would be the same. Now, we talked about ionic compounds, right? And when we write ionic compounds, we want to make sure in the simplest way possible, the charge equals 0, right? All the positive guys cancel out the negative guys. All ionic compounds, ionic formulas, they are always empirical formulas because that is how you write a proper ionic compound. You want the simplest way to get to 0. And in doing so, that means that basically all ionic compounds are empirical formulas. So they always should be that simplest ratio. Why do you have one over the other in practical application? It is in lab, for example, maybe you don't know what the compound is, but you could do a very simple experiment like we'll do maybe on Thursday, I think it's scheduled. You can do a very simple experiment where just by measuring masses, you can experimentally determine the empirical form of a compound, which is very easily done in the lab. And from that information, you can obviously calculate other things. So oftentimes the empirical formula can be very easily found in the laboratory by doing just a very simple mass measurements. And the difference is when you started with a mass and ended with mass, you calculate like the empirical formula. So that's a very common sort of laboratory procedure in terms of that difference. Questions on the difference between those two. All right, so here's again an example, N2H4. When we look at this, that's basically 2 nitrogens for every 4 hydrogens. That's a 2-to-4 relationship. You can divide everybody by 2, gives you a 1-to-2 relationship. And that would get us to our empirical formula here of NH2 for our molecular formula of N2H4. Again, only the molecular formula is the one that tells you exactly how many of each of those elements are present. The empirical formula is just going to give you really the simplest whole number ratio of the elements that are present. And as I mentioned a second ago, things like water, for example, is an empirical formula. NH3, which is ammonia, also an empirical formula. You can't get any more reduced down than that and still have whole numbers, as this is basically a 1-to-3 relationship, a 2-to-1 relationship, and a 1-to-2 relationship. There is no way to reduce those down and still have whole numbers. So again, sometimes the empirical formula and the molecular formula are the same. So why don't you take a moment for each of these? What would be the empirical formula? Okay, let's take a look. So on the first one here, we basically have 2 carbons for every 2 hydrogens. That's basically a 2-to-2 relationship. We can reduce, obviously, these down and still get whole numbers of 1-to-1, which means our empirical formula should be just 1 carbon and 1 H, which would represent the simplest whole number ratio of what's present. Question on that one then. Look at the next one, diiodine pentoxide. Here we have 2 iodines for every 5 oxygens. That is basically a 2-to-5 ratio. That is as low as you could go, right? There's no way to divide that out and still get whole numbers. And that's the key. Again, they do have to be whole numbers. The guys on the bottom there can't have any decimals or anything like that. So that would mean in this case, our empirical formula would actually be the same as our molecular formula in this case. Questions on that one. Lastly, a little glucose, that is 6 carbons for 12 hydrogens for 6 oxygens. That's a 6-to-12-to-6 relationship. You could hopefully see that you could divide everybody here by 6, and that would get you a 1-to-2-to-1 relationship. That means our empirical formula CH2O in this case would be our empirical formula. Question on that one. All right, the next we're going to talk about is percent composition by mass. And percent composition by mass is basically we take the percentage of whatever element we're looking for would equal the grams of that element in the grams of the molar mass of the compound times 100%. So we can figure out the percentage of each of the elements that are present by doing that calculation. So let's take a look at one here together. Ooh. So let's say we were doing hydrogen peroxide. So the first thing that we'd want to do is get the mass of hydrogen peroxide, the molar mass. And again, as we've been talking about, we could get that from the periodic table by looking obviously at the number below the symbol on there. So to get the molar mass of this guy, we would have 2 times the molar mass there of hydrogen. We're going to add it to 2 times the molar mass of oxygen, which is 16. And that's oxygen. And that's going to give us a molar mass in this case of 2 times 1.008 plus 2 times 16, about 3402 grams per mole. So in this particular case, I want the percentage of hydrogen. And in this case, we do have 2 hydrogens. So we take our 2 times 1.008 grams per mole, and we divide it by the molar mass of the entire compound, 34.02 grams per mole. We're going to times it by 100%. That is going to get us here 2 times 1.008 divided by 3402 times 100. That's something like 5.0 0.926% hydrogen. So by mass, basically hydrogen peroxide is made up of about just under 6% hydrogen by mass. We could do the exact same calculation for our oxygen. We also have two of them, so we'll take 2 times the mass of oxygen divided by the molar mass of our entire compound that we got from the periodic table times 100%. And that would get us basically 32 divided by 3402 times it by 194.06% oxygen. By the way, by mass, which one is makes up most of the mass here? It is basically 94% oxygen by mass, right? And about by 6% by hydrogen. By the way, since these were the only two elements present, did I really need to even do the second calculation? I could have just took, we know if we have all of our elements, that should equal 100%, right? So I could have, for the percentage of oxygen in this case, took 100% minus 5.926%, give or take with some rounding, should have got you there as well. So you could have alternatively done that for the last one present, or obviously you could do the calculation as well. That would get you there as well as you go through questions on that one. All right, so why don't you do the percent composition of each element for the empirical formula, which should be the next slide, I think. Scott. So what is the percent of hydrogen? Okay, so let's take a look here at the empirical formula, and we'll do our percent of hydrogen. In this case, in the empirical formula, we just have one hydrogen. So that would be 1.008 grams per mole. We do want to divide it by the molar mass of our empirical formula. So that would be 1.008 grams per mole plus our 16 grams per mole. And that's going to get us a molar mass for our empirical formula here of 1701, we'll call it. So that is what we would divide here by. And again, times it by 100%. So we'll take our 1.008 divided by our answer, times it by 100. And that's going to get us 5.927% here, hydrogen. We'll do the same thing here for our oxygen. In this case, we also have just one oxygen. So we'll take 16 divided by the molar mass of our empirical formula, not our molecular formula. And again, dividing it out there is going to get us about 94.06% oxygen. Was the empirical formula same or different than the molecular formula? Pretty much was the same, yeah. And that makes sense because, again, they are related to each other. The empirical formula is the simplest whole number ratio of what's present. And by mass, that means you basically have the same mass to mass ratio. So you can calculate the percent composition for your empirical formula versus your molecular formula, and it should come the same for each of the elements because it is the same ratio by mass that's present. Question on that one. Yeah. 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 It would still be right. Yeah, that's good. Yeah, and again, there's some rounding, obviously, with all this, so you should be pretty good. Yeah. Other questions? Now, I want to try another one here. That's not that. So for this one, what is the percent composition by mass of hydrogen, phosphorus, and oxygen? So hydrogen, again, 1.008 from the periodic table. Phosphorus, 3097, I think. And oxygen, still 16. Okay, so let's take a look. So once again, we want the percent composition of each of the elements in here by mass. So always, in this case, you do need the molar mass, obviously, of the entire compound. So that's where we're going to start. We got 3 times our hydrogen, or 1.008 grams per mole. We got just one phosphorus at 3097 grams per mole. And we do have 4 oxygens, each at 16 grams per mole. Again, just adding up all the parts there. That's going to get us 3 times 1.008 plus 3097 plus 4 times 16. Looks like a 9799 here. grams per mole. Now we're ready to do each of our percentages. So we'll start with our hydrogen. So again, in the formula, there are 3 hydrogens. So we need to take 3 times our 1.008. We want to divide it by the molar mass of the entire compound here. And which times it by 100%. And that's going to get us here 3 times 1.008 divided by 97.99 times it by 100. Going to get us a 3.086% hydrogen. We can do the same thing here for our phosphorus. So percent phosphorus, there's just 1 phosphorus, so that's 3097 grams per mole, divided by the molar mass of the entire thing, 97.99 grams per mole. Times it by 100%. And that will get us 3097 divided by 97.99. Times it by 100, like 31.61% phosphorus. At this point, you can, again, you have 2 of the 3. You could add those together, subtract 100 from it. Or you could just do the calculation for the last guy, just like the others. 4 times 16 for the oxygen, divided by 97.99 times 100%. And that's going to get us here 4 times 16 divided by 97.99. Times it by 100, going to get us 65.31% oxygen. Once again, obviously, when we do add up all of our percentages there, we should be in the ballpark of 100%, which we are, just slightly over, and that's good as well. So you definitely should be in that ballpark. Any questions on percent composition by mass? Okay, so one of the places where we do use percent composition by mass a lot is when we're actually asked to calculate the empirical formula from information. So if you are not given the molecular formula and you're just asked to calculate the empirical formula, there's a few steps that you want to do and follow. So let's talk about the steps to calculate the empirical formula. So very common, for example, is you are given the percent composition of the elements in this compound. So one of the most common things a lot of times is you are given, like I said, the percent composition of elements. And one of the ways that we can convert a percentage into a usable number is to assume that you have 100 of something, right? So a lot of times when you're given that information, we oftentimes will assume we have 100 grams of whatever we're dealing with. The reason we assume we have 100 grams is it keeps the percentages and the grams the same number, right? So if you have 50% by mass and you have 100 grams, you have 50 grams, right, of that thing, right? You got 20% by mass, and you got 100 grams, you got 20 grams of it. You can assume as much grams as you want, but the numbers would change. It makes it harder on yourself, so you don't want to do that. You just assume 100 grams. Now, whatever you're given, basically, you need to get those things into grams. And again, that's probably most commonly what we just talked about there, a way to do that. Once you have them in grams of all the elements that are present, the next thing you're going to do is convert grams to moles. So as we've been talking about, the way we convert grams to moles is the molar mass, right? From the periodic table is our conversion factor to do that. So now you're going to have all the moles of each element. So let's just say you did step number 3 here, and you converted everybody into moles by using the molar mass. And let's just say that you ended up with 2 moles of A and like 4 moles of B, this imaginary compound I just made up opposite. Once you've converted everybody into moles, the next thing that you want to do is divide by the smallest number of moles. So in my example above, I had 2 moles of A and 4 moles of B. Obviously here you could see that the smallest number is which one? It is 2 moles. So what we would do is take this guy and divide it by 2. And we would take this guy and divide it by 2, as that is the smallest number of moles. When I do so, this is going to equal 1, and this should equal 2. I just hit whole numbers when I did that, right? And if you hit whole numbers when you do this, and you divide by the smallest, congratulations, that is your empirical formula. And my empirical formula in this case would be AB2. So you want to get whatever they give you into grams. You then want to convert those grams to moles of each element. You want to divide all the element moles by the smallest number of moles. And if you hit a whole number for everybody, that would be your empirical formula. There's something question on it. Now, let's just say, though, we did step number 3, and we had 2 moles of A, and we'll go with 5 moles of B, right? And let's just say we have that situation that basically developed. Here, the smallest number of moles is still 2, so we would divide everybody by 2. So I'll divide this guy by 2 moles. I'll divide this guy by 2 moles in this case, right? Now, when I divide those guys by 2 moles, I do get 1 here, but over here I get 2.5, yeah? And that would give me an empirical form of A, B, 2.5. Remember, we talked about this bottom numbers are the moles, right? So that's why we're divided by moles, right? So that's what these are. Can I have like a half of atom of something? I cannot. So this would not be the correct empirical formula because we do not have whole numbers. They have to be whole numbers. Now, this is the question everybody asks, which is, can I round? And the answer is no in this case. This is too far away to round. The only time you could really round is if you're really, really super close to the whole number. Like you ended up with like 1.99 or 1.98, you could round that to 2. Or you ended up with like 2.03 or 2.05, you could round that to 2. But if you're somewhere like we are here, like 0.5, and the common ones that you come across are probably these, 0.33, 0.5, you end up with a number that's got one of those sort of decimals. Those are kind of in the middle, right, of the numbers, so that is too far to round. So what you have to do is figure out a number that you can multiply that guy by to get to a whole number. And what I mean by that, for example, if I took 2.5 and times it by 1, I get 2.5. If I take 2.5 and times it by 2, I get 5. And that would be the factor by which you need to multiply not just that guy, but everybody by to get to the empirical formula. And my new empirical formula would be A2B5 would be my correct empirical formula by multiplying, obviously, 2 times 1 and 2 times 2.5. So if you are too far from rounding, when you divide by the smallest number, you do need to figure out a number to multiply, not just the one that's a decimal, but everybody in the formula by that common number to get to the proper empirical formula. Question on that. So those are your kind of your 2 options. Either you divide everybody by the smallest, you get whole numbers, you're good, or really, really close to a whole number. Or if you don't, then you got to find that factor to get it to a whole number. Questions on that. All right, let's take a look at one here and see. So let's go through this one together here to talk about what we want to do. So we have ascorbic acid, which is vitamin C. It's composed of 40.92% carbon, 4.58% hydrogen, and 54.5% oxygen. We want to know what is the empirical formula. See, that's somewhere. Yeah, yeah, there it is up on top. So the first thing you definitely want to do in this case is, like normal, I want to look at all my percentages. And again, they should add up to 100%. And in this case, they do add up pretty close to 100%. If they do not add up to 100%, you are again probably missing an element somewhere. Yeah. So There would be, again, some information to allow you to figure out what you're missing, but you always want to make sure it does add up to 100% for sure. So basically we have, in this case, 40.92% carbon. We have 4.58% hydrogen, and we have 54.5% oxygen by mass. This is basically the percent composition by mass calculation we just did. So in this case, the first thing I want to do is get these guys into grams. So I'm going to assume 100 grams. And what that's going to do is essentially just turn my percentage into grams. So I would have then 40.92 grams of carbon. I would have 4.58 grams of hydrogen, and I would have 54.50 grams of oxygen. And again, basically by assuming 100, it's just going to keep all the numbers the same and make it much easier. The next thing I need to do is take the grams and convert them to moles, right? And we know how to do that. We've done a number of times today. That would require me to go to the periodic table, right? And get myself the molar mass of each of these elements that are present. That's 16. And use the molar mass from the periodic table. So that's the next thing I'm going to do. I basically want to get everybody into grams. I then want to convert into moles. So 12.01 grams per mole. This is the periodic table from the molar mass from the periodic table. For hydrogen, it's 1.008 grams per mole. And for oxygen, it is 16 grams per mole. So this is going to now convert me into the second thing I really need to do, which is get moles of everybody. So in this case, if I take 40.92 divided by 12.01, that's going to give me 3.4072 moles of carbon. 4.58 divided by 1.008, going to get me 4.5437 moles of hydrogen. And 54.5 divided by 16, 3.40, and we'll call it 63 moles of oxygen. First off, any question up to that point? We're getting to grams, molar mass, grams to moles. Yes, sir. I honestly, personally, this is not really my final answer. So again, just so you don't get into some weird numbers that maybe because of the way you rounded it, you end up like maybe I need to do like a common number to multiply by. So I would highly recommend trying not to round too much at this point, and that will kind of prevent those issues where you might just have some rounding error, which in the end, when you try to get to a whole number, might throw you a little further off than you want to be. And stuff like that. That would be my suggestion here. Definitely do not want to round, which is also a common error, super strong here. Yeah, so if you round really hard here, people always find themselves getting the wrong answer because of that rounding aspect of it. At this point, the next thing we want to do is look at each of these moles, and we want to divide by the smallest. In this case, it's fairly close, but it does look like the oxygen there just barely beats out by the smallest. So we're going to divide everybody by the moles of oxygen as it is the smallest, right? So we're going to divide that guy by 3.4063 moles, right? Moles here. And divide this guy by 3.4063 moles. Obviously, this is going to give us 1 when we do it. This will essentially give us 1 on the top as well. Again, not maybe perfect, but pretty darn close, I would think. Again, we get 1.0002, which is essentially 1. Here, we're going to get 4.5437 divided by 3.4063. That's going to give us a 1.33 in this case, yeah. At this point, our empirical formula would be CH1.33 and O. What is the problem with my empirical formula at this point? Yeah, that is not a whole number. And again, that 0.33 is too far to round. So here, what we need to do is what I mentioned a second ago. We just need to, figure out what we need to multiply to get us to pretty much a whole number. 1.33 times 1 is 1.33. That's not going to do it. 1.33 times 2 is 2.66. That's not going to do it. 1.33 times 3 is 3.99. 3.99 is pretty much close to 4. So that is okay in that case. Yeah, that's pretty darn close to 4. So what we would want to do is take that factor, which is a 3, and again here multiply not just this guy, but we need to multiply everybody here by that factor of 3. And if we do that, that's going to give us a C3H4O3. And now we have all whole numbers. And now we have our empirical formula at this point as well. Questions on that as well. So we don't have to worry about the other guys. Just have to worry about that. And it is possible, by the way, that you could end up with multiple ones when you divide by the smallest that are not whole numbers. But usually what that means is there should still be just one common number that will fix everybody. Yeah. So, for example, if I had 1.33 here and like 2.33 on the other guy, you can multiply everybody by the same sort of common number, and that should fix all the problems usually in those cases. Well, good questions on that there. All right, so again, these are the steps that you want to follow to do that. I think we'll lay it up there for today.